Gone, please.
Okay. And first of all, I would like to tell you that I am very happy to discover your institute and also to discover for the first time Rome, which is gorgeous city, in my opinion, one of the most important cradle of our modern civilization. And I understand that you have so huge institute because your country regularly faces some hazardous events like earthquakes and tsunami. And I would like to start just to mention that if tsunami are catastrophic events able to destroy many human structures and to kill people and animals, it's also at the geological time scale instantaneous event. Okay, next please. And tsunami are very different from storm events. When you have storms also may reshape the coastal lines, the strongest storms, but it will never go inland no more than 200 meters. With a tsunami, it can be kilometers inland because due to earthquakes or volcanic eruption or caldera collapses or landslides, you have no more for landslides, but in case of earthquakes, you have a strong, the wave carry huge kinetics energy. And when the water depth decreases, a large part of this kinetic energy is converted into potential energy. And you have the height of the wave increases. And what we have, it's in a first stage, very fast incoming tsunami wave, followed by receding waters. And during this stage of backward, you have some sedimentary deposits, which are called deposits, backwash deposits. Next slide, please, for Marco. Here, I will finish my talk today with this example of La Graciosa Island in the Canary Archipelago, Spain. You have here, on this volcanic island, the example here of a backwash deposit. And if we focus on these backwash deposits, next, please. Okay, you can observe a lot of material of biological origin. Here, molluscs, sometimes are broken due to the energy of the wave. And also basaltic pebbles. All this material being cemented, by a mixture of clays and sands. Okay, next, please. The tsunami records through time is quite difficult to interpret because, in fact, if tsunami can consider that there are rare events, but their preservation is also rare. And it decreases when you go to the fossil record, because of erosion process, remodeling of the coastline. And if we look here for the 20th or 19th century, you have some quite common events. And after that, this fossil record becomes very rare, very scarce. Next, please. In terms of geographic distribution, it's possible to document tsunami deposits everywhere, quite everywhere around the world. Not only in seismic areas, but also, for example, in Australia, which is open to the Indian Ocean and Pacific Ocean. They can receive waves for which the source is very far due to earthquakes in these oceanic plates. I will show you 3 examples today. 2 in the Mediterranean seas, Crete Island, Sicily, and 1 very new. We discovered it last year with my French colleagues in the Canary Islands. Next, please. Okay, what I would like to show you that these tsunamiites are also interesting time machines to read the Holocene climate. Because when it's possible to have a precise date, we can have reconstruction of climate with proxy of isotopic origin. We use a stable oxygen isotope measurements of biogenic skeletal remains. It can be for the marine environment, it can be mollusk, marine mollusk, or it can be also terrestrial animals like vertebrates, like mammals, which are killed by the wave. And especially in the case of Crete example, you will see that we can reconstruct both air and seawater temperature. Next, please. Here, this is the first case study. You have along the Kiona Beach, you have an interesting deposits above probably Pleistocene sands, which is the former beach. Okay, and you know this is in the northeastern part of Crete Island, close to the small village Castro, which means in Greek the old village, the old castle, the old castle. So next, close view, you see on this fossil sand beach, you have here what was interpreted by Bruns et al. In 2008 as a possible tsunami deposit. I know that it is discussed. There are some people who don't agree with the interpretation of tsunami deposit. Next, please. Okay, when you look at the outcrops, you can see here the remain of the wall. Here are some pottery fragments whose shape and color is typical of the Minoan civilization. And in the clay matrix, you have many remains of marine mollusk shells. And also, you have Murex, Conus, Osilinus, still preserves the nacreous layer, and sorry, many remains of cattle, bolidae. Here you have a tooth and bone fragments. We use this material to reconstruct both marine temperatures with mollusk shell and air temperatures with tooth and bone remains. Okay. In fact, when we analyze the oxygen isotope ratio between O18 and O16, it's a paleo temperature, it's a paleo thermometer, sorry. If we, in the case of mollusk shell, if we know the composition of the surrounding seawater, okay? And we have also to know the composition of fresh water on the island, because this is the water that was drunk by the cattle. Okay, let's make some exploration of this island. Next slide, please. Important for the isotopic calibration, it's to collect in the present day coastline modern shells, and you can find the same species. Okay. Because of Minoan civilization, it was about 3,000 years ago. Okay. And you can see here modern Osilinus. You have the fossil ones and the modern ones. Okay. Next, please. We collected seawater samples, and here you have delta 18 values. Delta 18, it means that this is a number that geochemists use. In fact, this is the ratio between the heavy isotope, oxygen 18, and the light isotope, oxygen 16. And this is this value, this isotopic ratio, in fact, is referred to the global composition of seawater on Earth. Okay, and if you have a positive value, it's typical of the Mediterranean Sea because you have more evaporation than precipitation. Obviously, our sea has a negative hydrological balance, and when you are more evaporation than precipitation, and the molecule of water vapor that contains the light isotopes incorporate preferentially the water vapor in the clouds, and the heavy isotopes remain in the liquid water. Okay, this is due to small differences in the vapor pressure between the heavy molecules and the light molecules. This difference is not so huge. It's close to 1%, but it's enough to make this isotopic differences between the two phases, vapor and liquid, in the water cycle. This partitioning of isotopes, heavy and light, we call it isotopic fractionation. Okay. And you can see here that we have values close to 1, and these values are nearly constant here. Here we are on this is the seawater close to the tsunami, the remain of the tsunami deposit, which is here. Okay. Okay, next, please. On the eastern side, close to Ambelos, you have, for example, you see delta 18 values always close to 1.9. It can change. You can observe some minor changes along the coast. Okay, next, please. Here, it's close to Scythia, in the northeastern part of the island. And it's common to find some springs. And you can measure the oxygen isotope composition of this fresh water. Of course, it's negative value, okay, because this fresh water is derived from rain, and it's condensation of clouds. And in clouds, you have more, relatively to the sea, you have more light isotopes than heavy isotopes, which means that you have negative values. And here, they are close to -7. Next, please. To springs close to Zakros, -7.3. You know, it's quite similar. And Zakros is a village very well known in Crete. And they are convinced that they produce the best olive oil in the world. You disagree, maybe? You Italian people. Next, please. As typically an example of such spring. Okay. Next, please. You have a lake in Crete. It's if you follow the coastline, it's really dry. Okay, but in some places, it's possible to find here a large mass of fresh water, the Cornas Lake, which have more negative value, close to -8. We will see why later. Next, please. Here, this is the Google Earth view of the Cornas Lake, and it's an important spot for bird migration in the Mediterranean Sea. Next, please. Close to Zakros was here, and here you have a beach, Zakros, and there are some fresh water with negative values, but not so negative, -6, and the sea is always close to 1. Okay, next. You can see here this small water pond and the sea here. Next, please. Okay, you have a view here of this small body of fresh water, and you can see here the sandbar and the Mediterranean Sea. Next. Okay, here you have the sea and this big sandbar. Next, please. Okay, just to have a few minutes in detail, this is a commonly used diagram by geochemists, by stable isotope geochemists. You have on the y-axis the ratio between deuterium and hydrogen isotopes for the water molecule. And here you have the oxygen 18 over oxygen 16 ratio. The thick black line, this is to be at the first order, all the precipitation on the world follows this straight line. Okay. It's a global property of the water cycle on Earth. But you have some regional differences. And this is the case of the Mediterranean Sea, because it has a specific hydrological and climatic range. And in fact, precipitation over the Mediterranean basin are on a parallel line, which is dotted here. And the green square correspond to the isotopic composition I just presented you before with the pictures. Okay. And you have here a few of them, which are clustered. And here, the highest value, close to the beach, you know, and the lowest value of the Cornas Lake. We will try to understand first how it works here, because you see this kind of water, maybe it suffered some local evaporation, and the value of the residual water will increase with evaporation, or it can be a mixture between Mediterranean seawater and fresh water derived from the precipitation. Here, small, the black dot, it means standard mean ocean water. This is the isotopic composition of the global ocean on Earth. And Mediterranean composition, you know, are above because of the dominating evaporation in the Mediterranean basin. Okay, next, please. And if you have, you can measure the salinity, the ratio between deuterium, hydrogen, O18, O16. For the 2 members, pure fresh water, a spring, okay, in that case, for example, the seawater, and you can solve this matrix equation quite easily. And we will see you can get a unique solution. And in fact, this is a mixing between fresh water and seawater with only 7% of seawater in the mixture. Now, there is a connection. Maybe there is an underground connection between seawater and fresh water. Or maybe there are some seawater that mixed with fresh water during storms, for example. Okay, next, please. Now we will try to understand why we have such negative values for the cornice lake. Next, please. This is due to an altitude effect. With increasing altitude, air temperature decreases, as you know. Okay, and there is an increasing isotopic fractionation between liquid vapor and water vapor. And for the Crete Islands, this is a symbol, is a diamond. We are here, and you know that at elevation higher than 1,000 meters, the isotopic composition, oxygen isotope composition of water is close to -8. Next, please. This is due to the distribution of relief in Crete. And the highest mountain in Crete are just here, and the cornice lake is just behind. Okay, and when you have these mountains, it acts as a water tower. It helps condensation of clouds and rain. Okay. Next, please. You have here the geographic distribution of precipitation on the island. It's important to interpret the fossil record. Okay, I give you all the basic elements here to understand the interpretations. As you can see, the maximum of precipitation occur at the maximum elevation. And along the coastline, especially in the eastern part of the island, it's quite dry. Okay. Next, please. Regarding air temperature in Crete, if we look at the record before 1990, here you have typically the beginning of the warming stage. You have quite a near constant mean temperature of 18.5 degrees. Okay, with a seasonal variation, with the coldest months, January with 12 degrees and July with 26 degrees. So just to keep in mind a few moments, please, these values, that will be useful. Next, please. If we look at the sea around Crete, you have the isotherm 20 degrees, which is close to the eastern part of the island. And remember that it's not so warm here in Crete because of the presence of cold water, because you have really deep water and cold current in this part. And in the north, you have the Aegean Sea, which is another cold water mass. And here, the seasonal variation, you have the minimal seawater temperature recorded in February with 15 degrees and 25 degrees in August. Next, please. Okay, if we are during the, if this tsunami, some people proposed that it resulted from the caldera collapse of the present-day Santorini Island. That was called Terra Island by the Greeks before its explosion. And in the sedimentary deposits, you can find volcanic ash whose chemical composition is compatible with the basaltic rocks of the Santorini volcano. And this period is called by climatologists the Minoan warm period, and it was probably the warmest stage of the last 5,000 years, the second part of the Holocene. Okay? And this is deduced here from air temperature calculated from the stable isotope composition of ice cores in Greenland. Okay. Next, please. We'll see now the climatic record on the seaside. Next. We have isotopic fractionation equation that were established here by Grossman and Kuh in 1986. They were established for marine mollusks. Okay. If you know the delta 18 of water, it doesn't change the last 1,000 years. Okay. And we know that it's close to 1. I show you the measurements. You can analyze the aragonitic shell. It's calcium carbonate, the shell. And you can have the temperature using this slope and intercept values for the straight line. Next, please. And what we obtain is 2 frequency histograms. In blue, it corresponds to the present-day mollusk we collected along the seashore. Okay. And in red, this is the temperature calculated from the oxygen isotope composition of the fossil mollusk preserved in the tsunami deposit. We have here 2 normal distribution. It's interesting because it means that it's compatible with the presence of only 1 population. Okay. And we obtain for the present day mollusk shell a mean temperature of 20 degrees. I like to say a mean temperature because, you know, when you collect mollusk shells, the dead animals, some of the shells may have been present for several decades. Okay, it's not instantaneous. In fact, with my colleagues, we had the strategy to collect some kind of stochastic sampling, collecting either dead animals or living animals. Because our idea is that we try to mimic what did the tsunami. You know, we collected the same dead animals, only the shells, and living animals. And it seems to be not too bad because, you know, the standard deviation for the fossil samples and the modern samples are rather similar and could correspond to some seasonal variations or interannual variation of the seawater temperature. Okay? And these 2 distributions are statistically different at the 95% level. And we have typically a 2-degree difference. During the Minoan period, it means that seawater was 2 degrees higher than today. At the beginning of this 21st century. Okay. Next, please. We can also look at seasonal variation. It's an important component of the climatic region. And you know that mollusk shells grow incrementally with time, and we can make incremental samples following the growth axis. And this we did here. Here you have the length from the umbilicus of the shell in millimeters. Under our latitude, the Mediterranean Sea, close to 35 degrees north, the input signal, it mimics a sine wave function. Okay, the seasonal variation. However, this input signal is distorted due to the growth of animal which change with ontogeny. You know that we grow faster during the juvenile stage and slower and slower with aging. And the growth of the shells is also dependent of seawater temperature. And next, please. To try to model this, I use this differential equation that was proposed for the first time by Ludwig von Bertalanffy in 1938, where I define in this paper organic growth at the measurable increase of an organic system in weight or length. And for example, today it's used to predict fish growth in fisheries. But we can apply this equation to the length of a mollusk shell, considering that x is the length of the shell at time t, k is a positive constant called the von Bertalanffy's growth rate, and L is the maximum length of the shell. Next, please. In the case of our data, we obtain this kind of curve. Okay, how we can obtain this? Because here, in fact, it's called relative elapsed time. Can you go back, please? One again. Yes. Okay. In fact, we have to make an assumption that here it corresponds to the cold season, and here the warm season. It means that we have annual cycles. Okay. And we can use this annual cycles as anchor in the time evolution. Next, this is why we can produce this curve. And this function we obtain by this cura approximation. Okay. May be used to correct the original signal, to try to restore the sine wave function. Okay. Next, please. And it gives this. It's not very good. I was really disappointed. I only made this this with one sample because it requires a lot of stable isotope analysis and it takes time. But we can infer that, okay, it's probably seasonal variation that triggers, that drive this isotopic variation. And it means that we have, for the coldest season, 16 degrees and 25 degrees from the warmest season. It's exactly what we have today. And could you go back again? Again. Thank you. As you see, maybe I pick up a sample in this part of the frequency histogram for the fossils, which, there is a common situation. Some years probably during the Minoan period, it was very similar to today. Okay. Okay, we can progress again. Now, again. Yes, we will look at the climatic record on the land side. As you know, here we are on the eastern part of the Crete Island. It's at about 200 meters of elevation. It's always dry. Next slide, please. And we analyze bone fragments and also the tooth of the bovidae. And we also make incremental analysis along the growth axis of this tooth. With mammals and the skeletals, what we can do? Mammals have constant body temperature, near constant body temperature of 37 degrees. Okay? It means that temperature does not hide any difference in isotopic fractionation. You have the composition, your skeleton in terms of oxygen, as the isotopic composition of what you drink. Okay? And it's very used in archaeology to track the origin of people, to track migration. Okay? An Inuit has an oxygen isotope ratio much lower than an Italian, due to the differences of composition in the precipitation. Okay? And we have this kind of relationship for all herbivorous mammals. With the increase of oxygen isotope ratio of precipitation, you have a linear increase of the oxygen isotope composition of your skeleton, both bone and teeth. If you include seasonal variation with a bootstrap technique, okay, you can infer more robust relationship we can apply. If we analyzed the oxygen isotope composition of the tooth or bones, we can estimate the oxygen isotope composition of the water drawn by the animals, and generally its precipitation is derived from precipitation. Next, please. And the oxygen isotope composition of precipitation is also triggered by changes in air temperature, because temperature controls the magnitude of the oxygen isotope fraction. And here, for the Mediterranean basin, we have this relationship. And when you report the oxygen isotope value of rainfall on this line, you have an estimate of the mean annual air temperature. Okay? Next, please. For this tooth, we made a few points. It's incremental sampling of this tooth. And we obtained the lowest temperature value of 15 degrees and the highest of 23. And in the present day situation, the coldest month is 12, but it's not surprising to have something higher during the Minoan period. But the warmest month is 26 degrees. And here we have no higher than 23 degrees. And there is an explanation for this gas. It's just an example to show you the limit of the method. Okay. Next, please. Remember here the distribution of precipitation. The tsunami deposit is here. And in fact, during summer, there is no precipitation. No precipitation, it means no record. In fact, during summer, probably the kettle was watered by water collected during the spring. Okay. And we have a missing part of the record. The warmest temperature cannot be recorded because there is no precipitation during summer in this kind of island. Okay, next, please. I will start now with case study number 2, maybe more exciting for you, I don't know, because it's located in Sicily. We went to the field last year with Paolo, Marco, and Alessandra in the Pantano Morghella area, south of Syracuse. Next, please. And at the end of the summer, this inundation plain, there is a river and fresh water with birds during the winter, and it's dry. Next, please. And this is a good period to perform coring. And here it was published by your team. And you have the position here of all this coring. All was mapped here in this plane. And here you have the Mediterranean Sea, and here the Morghella Beach. Okay, and well, okay, it's in inverts, but the shells, some of the shells of Cerastoderma, mollusc shell, it was dated by the C14 method between 270, 600 after Christ, and with simulated luminescence, it's very close to 370. Okay, and it's not a demonstration, but it was just proposed that a specific layer, a sandy layer between a few centimeters 6 up to 20 centimeters 6, between clays deposited by this kind of big pond, lagunal system. This sand was carried by a tsunami wave, okay, and could correspond to the Crete earthquake that was dated of July 21st of the year 365 after Christ. Next, please. And there are some chronicles, for example, with Ammianus Marcellinus, who reported that ships were perched on the roof of houses, as happened at Alexandria in Egypt, and when with waters that were expected to kill many thousands by drowning, tides, and it's compatible with a tsunami event and not only a big storm. Next, please. And this is what we did last year at the beginning of September to make a few new cores close to what you did. Two main core S20 and S7 in the central part of the plane. And you can see here this sandy layer with here the clays. And which is characteristic. Next, we have not the same organism inside. In the clays, we have some for example, foraminifera, which are compatible with low energy freshwater to brackish water environments, ostracods as well, like Cypraeus torosa. And in sandy layer, we have mollusks like Loripes, Hydrabia, or Cerastoderma. and also foraminifera that are typical of coastal marine waters or offshore environments. Okay, this aspect, we want to say that the sound is marine. It was carried by the wave up to 1.5 kilometers inland. Okay. And what I started to analyze with the help of CNRS funding and its interdisciplinary program. I received fundings to study these samples. And next, please. First, we check the preservation of the mollusk shell. It remains pure aragonite. It was the same in Crete. It didn't precise that, but the same. And with Raman spectrometry, it was possible to check that it was still aragonite without a trace of recrystallization for the 3 studied species. Next, please. And after that, we made powders, and with a mass spectrometer available at Università Claude Bernard Lione, we calculate the famous oxygen isotope ratio. And next, please. We use the same fractionation equation, and we applied for Crete. And using the delta rating of the surrounding seawater, we make a few samples of the seawater, and we obtain a mean value of 1.7. It means that in this part of Sicily, seawater suffered much more evaporation than in this part of Crete. Okay. And next. We are here just looking at the oxygen isotope ratio for the 3 species. As you can see, we have 3 different, in fact, especially one hydrobia. The mean value, it's not really a mean value because it's not a normal distribution, but it's a problem. Okay. But the median value is really different from those obtained for Cerastoderma and Loripes. Next, to show you now when we convert into temperature. Next, please. Okay. And you see for hydrobia, we obtain 14 degrees. It's impossible. It's too low. And this is a problem, you know, that we have many samples that indicate too much low temperature. And in fact, the problem is that the assumption that this organism lives in seawater with a delta rating of 1.7 is probably wrong. Because hydrobia tolerates a large range of salinity from a few per mil up to 70 per mil. And it makes wrong assumption we use. Okay, it's much better with Cerastoderma or Loripes. In fact, in my lab, we continue analyzing more samples because we need more samples to refine the statistics. It's possible that these two mean values converge, in fact, between Cerastoderma and Loripes. But Loripes, we know that this is really a marine mollusk living between the surface and 10 meter depth. And for this one, we obtain 19 degrees. And what is really nice, that you can find Loripes in the present day seashore. Okay, next. Okay, we found it was just to make a first shot with 12 samples. We will collect more this year, okay, to refine also this calculation. But if we compare same species, Loripes, you see that now it's 23 degrees instead of 90 degrees during the tsunami deposit. There is a 4-degree difference. It's quite robust. Maybe we say that it is a 3 or 3.5 or 4.5 in the forthcoming months, but it cannot be very different. Okay. And next, please. This temperature is really compatible with the temperature of 22, 23 degrees you have close to the southeast coast of Sicily. Here it's for June, and June or November samples the mean annual temperature. And next, please, Marco. And here, this is a work produced by Lundquist in 2010. He made a synthesis of numerous temperature-sensitive proxies in the Northern Hemisphere. And you have this kind of record. Here it corresponds to the warm Roman period. Okay, here it's a medieval warm period. Here it's the Little Ice Age. And the Morghella tsunami deposit fits in terms of time with the beginning of this cold stage called the Dark Ages. Okay. And next, please. Really of interest is this speleothem oxygen isotope record in Southwest Island, which is here, and compared with the delta 18 variation in the Greenland ice cores. And you can see that we are still here at the beginning of this cold age, dark ages, between the Roman 1 period and the medieval period. And these 2 per mil difference in the speleothem composition correspond to a 3-degree difference in air temperature. Okay? Keeping in mind that our 4-degree difference includes the last warming period, you have to remove 1 degree in excess. Okay. We have to refine what I show you. We have to refine this with more isotopic analysis. I also plan to analyze the foraminifera, whose species are known to be strictly marine. Okay, and we will be able, when we publish this study, to have a more precise, more refined picture of this climate record. But it's interesting because it's tsunami event most likely do not correspond to the warm period, the Roman 1 period, but the beginning of the Dark Age. Okay, next. Just a few slides to finish. It is not too long for you. Last year, with 2 French colleagues, and you know one, Raphaël Paris and Franck Laverne, who are specialists of tsunami deposits, we went to this small island, La Graciosa, which is north to Lanzarote Island, no more than 200 kilometers of the Western Africa coast. Next, please. Yes, some Spanish people told us that maybe there is a tsunami deposit, but never documented. And La Graciosa is a small volcanic island. You have the volcanoes here and here. But it's difficult to map this area because it's covered of sand coming from the Sahara. You know, that's sand that's carried by the trade wind. And here you have the northern part of Lanzarote Island. And you have a small city here, no more than 700 people. And during summer, it can be 2 or 3 times higher because of some tourists. Because you have really beautiful spots and beaches here. Next, please. Okay, and we explore all the coastline. And these are the sampling sites. This one, we don't know exactly what is this, but these are the sampling sites. Okay. And next, please. When you walk on this area, in fact, you can find some remains of the distal facies of the Tsunami deposit with a large mollusk shell, patella, okay, and basaltic pebbles coming from a beach, okay, and it marks the limit of the waves, what we call the run-up, maximum promise of the wave on the island. Next, please. And here it's close up to the famous proximal facies, close to the seawater, to the shoreline, the present-day shoreline. I show you a similar picture at the beginning of my talk. Okay, it's a backwash deposit when the water is receded. C14 dating is in progress. Maybe it corresponds to the Roman warm period. We know that a Spanish paleontologist found one goat tooth. It means that there are already some cattle and presence of humans. It cannot be so old. And it was this tsunami happened before the installation of the village, because you have traces of the Tsunami deposit behind the village, around the village. Okay, and next now. Okay, compiling all the GPS measurements. There was a flying drone. And in pink, this is the area which correspond to the flooding by the tsunami, with a maximum run-up estimated close to 20 meters above sea level. And our interpretation that this tsunami deposit was provoked by the collapse of the Famara mountain. You know, there is a big scar. And next, you will see with a picture. Here you have the big remnant of the landslide. Okay. And we estimated with satellite picture the volume of material and the energy carried, and it's compatible. I do not perform that myself. It's moving. It's okay, it matches. I believe in, because I know it's very strong. Okay, next. And to conclude, I would like to thank especially Paolo, Marco, and Alessandra. We spend exciting time. This is the first time of my life I perform manual crawling with Paolo, Marco. I learned many things with them in the field. And sometimes you smoke a cigarette. I smoke some Italian cigars. Okay, thank you to both of you, and thank you for your welcome in this famous institute.
Okay, thank you, Christophe. Now, if there is any comment, question, or suggestion, also from the audience that is connected through the meet, we may obviously have Christophe answering. I don't know, but show up on the chat or with your microphone. In the meantime, if not, anyway, I really would like to thank Christophe for all this talk. We also learned a lot working with him because they say that geochemistry is something that we would like to know better, but we don't know. And so having a professor like Christophe with us was really exciting. We also share different experience worldwide in the field, comparing experience, work in the field and technique for sampling and stuff like this. We have been pleased to be invited to join his project, and that's it. We hope to do our best in the future and to produce nice record of paleo temperature by using the tsunami deposit we know and those also that we are going to find. If there is no question, we may stop here for now. Thanking Christophe again and see you soon. For all the folks listening, this is the end of the seminar. I'm going to stop the recording, and thanks, Alessandro. There is some thanks from the chat I want to share with Christophe. And at the end, I want simply to mention that Christophe will be here also on Thursday. So if somebody just want to be in contact with, please email me or phone me, and I will try to do my best to put Christophe in contact with you. Okay? I'm stopping the recording.